Hello, my name is Dan Alexandrescu. I'm the CEO of IRAC Technologies, a company providing tools and solutions for the management of the reliability of complex electronic devices and systems. An important requirement is that today's devices are expected to function correctly during the projected circuit lifetime over a large range of operating conditions and workloads without failures and performance degradation. A key aspect of this continuous expected reliability is semiconductor aging. Phenomena such as hot carrier injection and bias temperature instability can change the electrical properties of transistors and cells, affecting the performance of the device. The aging problem is getting worse with aggressive technology scaling, process variations, dynamic operating conditions, and increased circuit complexity and size. The semiconductor industry needs efficient solutions to manage aging issues in today's sophisticated devices. Firstly, technology providers and device physics experts are working hard to provide a clear understanding of physical phenomena and its impact on the character of transistors and gates. Furthermore, aging information needs to be provided in the design and manufacturing flow through adequate reliability data exchange formats such as RIF in order to be used by designers and system architects during the specification and implementation of reliability features of the system. Obviously, EDA tool support is an important requirement for any data exchange, aging analysis, or improvement. Therefore, the collaboration of all the partners from the design manufacturing flow is absolutely needed. As an example of such process, the MORVI project is a research and development undertaking focused on semiconductor aging and process variability, integrating experts on technology, device physics, circuit and system designers, EDA tool providers, and end users. The overall goal of the project is to provide accurate aging models for transistor, logic gates, and blocks, predicting the design performances over the projected lifetime. The next step consists in managing the aging issues, allowing continuous reliable system operation at the required performance levels. Degradation affecting delays on standard cells can be mitigated through guard banding. Particularly, one-time worst-case guard bands are typically added by the design during the specification or design flow. Obviously, reducing the guard bands is a critical issue for the semiconductor industry from a performance or competitive perspective. Accurately characterizing the circuit aging is a requirement for an effective and frugal guard banding. However, removing the guard bands completely is even more attractive for the industry. Techniques such as self-calibration and self-tuning can progressively compensate circuit aging over the circuit lifetime. In addition, these techniques can be the key for continuous performance, reliability, and low power consumptions in today's power-conscious mobile and high-performance computing. Self-calibration and self-tuning techniques consist in dynamically adjusting local and system parameters such as voltage, frequency, biasing to the performance requirements, workloads, environment, and aging. They rely on physical data provided by embedded test instruments, sensors, and monitors. The academic and industrial community provides a wealth of solutions to detect or predict timing errors induced by aging. Of a particular interest to the industry, pre-error monitoring and error detection can be implemented using double sampling approaches. This approach allows detecting temporary faults, timing faults, transient upsets at very low cost and can be used to adapt the clock frequency of the circuit to the degradation of the circuit delays, supporting a successful implementation of the self-tuning architecture. Double sampling architecture helps mitigate numerous flaws concerning nanotechnologies such as PVT variation, accelerated circuit aging, soft errors, power dissipation, and thermal issues. In conclusion, there are many interesting challenges associated to the aging of semiconductor devices, and the industry needs a very good understanding of the physical phenomena, the supporting EDA infrastructure, and efficient solutions to implement advanced self-tuning devices able to work reliably over the projected lifetime of the system. Thank you for your attention.